In 1807, Jean-Baptiste Joseph Fourier discovered a way to describe the periodic signals as a sum of weighted sinusoidal signals or phasors. This description is known as the Fourier Series expansion, abbreviated as FS. The application of the Fourier series became important in many different fields, for example, electrical engineering, vibration analysis, acoustics, optics, signal and image processing, quantum mechanics, economics, etc. In this video we will give a short conceptual derivation of the Fourier series expansion, which consists of two parts, namely the Fourier synthesis and Fourier analysis. In the synthesis part we will show that any periodic signal can be decomposed as a sum of weighted phasors, in which the weights represent the spectral components of the periodic signal. In the analysis part we will show how to calculate these weights for a given periodic signal. In order to come to the Fourier synthesis equation, we will first investigate if the addition of periodic signals is again a periodic signal, and if so, what is the period? In this first example we add two periodic signals, one of 6 Hz in red and one of 2 Hz in blue. From the plot of the added signals in black we can verify that this signal is periodic and that the period t0 equals half a second. Mathematically we can find the same result by using the greatest common divisor operator, abbreviated as GCD. Taking the greatest common divisor of 2 and 6 Hz results in F0 of 2 Hz. This implies that both frequencies of 2 and 6 Hz fit an integer time into the added signal of 2 Hz. When adding a third signal of 1.2 Hz in purple, we obtain a new signal, denoted as xp of t. Applying the greatest common divisor operator to the frequencies 1.2, 2 and 6 Hz results in 0.4 Hz. In other words, the composed signal xp of t is a periodic signal which repeats every t0 is 1 over f0 is 2.5 seconds. The reason for this periodic behavior is that all three individual signals have a frequency which is related by an integer factor, or harmonically related, to the frequency f0 of the composed signal xp of t. Namely, the 1.2 Hz signal in purple fits 3 times in one period of xp of t. The 2 Hz signal in blue fits 5 times in one period of xp of t, and finally the 6 Hz signal in red fits 15 times in one period of xp of t. This reasoning results into the following discovery made by Fourier. Any periodic signal xp of t with fundamental period t0 is 1 over f0 can be composed or synthesized with a possible infinite sum of harmonically related sinusoidals. This formulation can be described mathematically as follows. This equation describes how a real periodic signal xp of t is composed of a DC component A0 plus an infinite sum of sinusoidals, each having amplitude a, k and phi k. Harmonically related implies that all frequencies of the sinusoidals are related by an integer factor k times the so-called fundamental frequency f0, which equals 1 divided by the fundamental period t0. The figure below shows an example of the periodic signal. A more compact way to describe this equation can be obtained as follows. Use Euler to write each of the sinusoidals as sum of two phasors, then introduce a new variable alpha k, which combines for each sinusoidal its amplitudes ak divided by 2 and phase phi k. There's one exception. For the index k is 0. Alpha 0 equals the DC component A0. The periodic signal xp of t is assumed to be real, which implies that the amplitudes ak are real. As a result of this, it follows that the complex conjugation of alpha minus k equals alpha k. Combining all these results leads to this last expression, which shows that any periodic signal xp of t can be composed or synthesized as a possible infinite sum of weighted harmonically related phasors. The weights alpha k represent the spectral content of the periodic signal xp of t, as denoted in the last figure. In order to show that it is important that the frequencies of a periodic signal are harmonically related, the following example. Assume a signal xt consists of a sum of three sinusoidals with respectively frequencies f0, k1 times f0 and k2 times f0. When the parameters k1 and k2 are integers, the result is a periodic signal xt. For example, when k1 is 3 and k2 is 5, we obtain the figure as depicted below. However, when choosing irrational numbers for these parameters, the resulting signal xt is not periodic anymore. In order to show this, we choose for k1 and k2 irrational numbers as follows. k1 is chosen as square root of 8, which is approximately equal to 2.8, and k2 is chosen as the square root of 27, which is approximately equal to 5.2. Although the values of the parameters of this signal x of t are close to the values of the parameters of the previous example, the resulting signal is not periodic anymore. Up to now, we've seen that any periodic signal xp of t can be composed or synthesized as a possible infinite sum of harmonic related phasors, each weighted by a complex number alpha k. The next question to answer is, how can we find the values of alpha k, or in other words, how can we analyze the spectral content of the periodic signal xp of t? For this, Fourier used the following Phasor Integral property, which is an integral over one fundamental period t0 of a phasor with frequency k times the fundamental frequency f0, and the result is divided by t0. This Phasor integral property is shown in the following animation, which shows the surface below the projected real and imaginary components of a phasor, in which the phasor is represented as a rotating vector. When the surface counts positive to the integral, it is colored blue. Otherwise, when it counts negative, the color is red. From the animation, we can clearly see that the total amount of red and blue area is the same. This implies that the total surface, integral, over a number of rotations is equal to 0 for any frequency which equals an integer number k times the fundamental frequency f0. There is only one exception, and that is when the integer k is equal to 0, which represents frequency 0. How this Phasor property can be used to find the frequencies of a periodic signal is shown in the following animation. In this animation, the periodic signal xt consists of a sum of two unknown sinusoidals with related frequencies, a 1 Hz signal with amplitude 2 and a 3 Hz signal with amplitude 1. These two signals are represented in the complex plane by a blue and a brown rotating vector respectively, which are added in a vectorial way. For simplicity, we only show the projection of the rotating vectors on the vertical axis. This periodic signal x of t is multiplied with a phasor, which is denoted by a green rotating vector. The projection of the multiplication of the green phasor with the sum of the two phasors of x of t is shown in the figure in the middle. The resulting surface, which represents the integral, is plotted in the figure at the right hand side. When multiplying the signal x of t with the green test phasor with frequency 0, the result is 0. Periodic signal x of t does not contain DC. When testing signal x of t with the green test phasor of frequency 1, we can clearly see that one of the phasor components of the periodic signal xt, namely the 1 Hz component in blue, has the same frequency as the frequency of the green test phasor. As a result of the phasor property, this leads to a non-zero result. There is no frequency of 2 Hz in x of t. The result of the integral is 0. While the frequency of 3 Hz in red is triggered when the green test frequency is also 3 Hz. The resulting integral is again non-zero according to the phasor property. Furthermore, there is no frequency of 4 Hz in x of t. Finally, the same reasoning follows for all negative frequencies. And in general, this leads to the given mathematical equation, which can be motivated as follows. By multiplying a periodic signal xp of t with a phasor with frequency k times f0 and taking the integral over one period t0, the result of the general phasor property is that only the frequency k times f0 of the periodic signal xp of t is triggered when it's present. In case the frequency k times f0 is present, the integral results in a measure, alpha k, representing the frequency content of the periodic signal xp of t at frequency k times f0. When this frequency k times f0 is not present in the periodic signal xp of t, the value of alpha k will result in 0. As a result of this general phasor property, we obtain the following analysis equation of the Fourier series expansion. The Fourier series are defined for periodic signals xp of t with fundamental period t0, which equals 1 divided by the fundamental frequency f0 as depicted in the figure, while it's based on one period of the periodic signal xp of t. Such a periodic signal can only have harmonically related frequencies, which are equal to an integer number k times the fundamental frequency f0, which leads to a general expression of a periodic signal xp of t as a possible infinite sum of weighted phasors, as depicted in the figure. The weights alpha k represent the frequency content of the periodic signal xp of t. Concluding, when we want to evaluate the spectral content of an ideal periodic signal, we can use the Fourier analysis equation. For this we need the description for the periodic signal xp of t and its period t0. With the resulting weights alpha k, we can make a spectral plot of the ideal periodic signal. The frequency axis of this plot denote the frequencies of the harmonically related phasors, which are present in the periodic signal, while the complex values of the weights alpha k represents the amplitude and phase of these phasors. The other way around, any periodic signal xp of t can be synthesized or reconstructed as a possible infinite sum of weighted harmonically related phasors. In practice, this infinite sum will always be finite, and the resulting periodic signal will be an approximation of the original periodic signal. The more terms of the sum are taken into account, the better the approximation. Finally, we note that the spectral weights alpha k of a real signal have special symmetry properties. This can be shown as follows. By evaluating the analysis equation for alpha minus k, it follows that the negative sign in the exponent becomes positive. When taking out the complex conjugation operator, this positive sign becomes negative again, and the periodic signal xp of t becomes complex conjugated. When xp of t is a real signal, it is equal to its complex conjugated version, which results, in between brackets, into the original analysis equation for alpha k. Concluding, it follows that for a real periodic signal xp of t, the magnitude is a symmetric function, while the phase is an anti-symmetric function. This ends this video in which we explained the concept of the Fourier series synthesis and analysis equation. In a follow-up video, we will evaluate some very common examples. Thank you for your attention.